Good afternoon. I'm Anirban Basu. I'm a professor of health economics and the director of the Choice Institute. Before we begin, we ask those engaging in this event to reflect on the lands on which we learn, live, and work, and acknowledge all of the unceded ancestral homelands and traditional territories of the Coast Salish people who have been here since time immemorial. Welcome to the 2023 Annual Choice Symposium. The Choice Institute, which is hosted within the school in the Department of Pharmacy, is a premier hub of research and training in health economics at the University of Washington, Seattle, and globally. And very much like most scientific fields, we are faced with the enormous potential and the challenges of using data sciences and AI in our work. We have made several strides in getting data sciences in our curriculum in conjunction with health economics. That includes introducing a new degree option for our PhD students in data sciences. We will be introducing a new graduate course in the application of data sciences in health economics and outcomes research. And also will launch a graduate a certificate for working professionals on the applications of data sciences in HEOR. So this symposium highlighting the discussions and the cautionary tales of using AI and data sciences is quite timely. Before I call on our symposium chair, I would like to thank our choice manager, Ms. Marina Gano, and also Liana De La Torre for all their efforts in helping organize this symposium in such a great venue. And thanks to all our students who have helped with the organizational details of today. After the symposium, please join us for a small reception outside. Not at the Vista Cafe upstairs. But now, let me call upon the Associate Professor Asta Bansal to moderate the discussions going forward. Asta, thank you.
Okay. Great, thank you, Anirban. Hello, everyone. I'd like to offer my welcome as well to our annual Choice Symposium on the challenges of using AI and machine learning in healthcare. We've gathered a great diverse set of speakers today to explore the complex and ever-evolving landscape of AI's role in healthcare, with the goal of shedding light on some of the obstacles and opportunities that lie ahead. I will introduce our speakers in a minute, but to give you a sense of the agenda, we will start off with Mr. Mike Willingham, who will be followed by Dr. Noemi Krief, who are both here in person. Our third and last speaker will be Dr. Judy Gichoya, who will be joining us virtually. Each speaker will have the floor for about 30 minutes, and that will be followed by a moderated Q&A session. In terms of questions from the audience, we're happy to take any quick clarifying questions at the end of every talk. But if you have more substantive questions, we ask that you please hold them till the end for the Q&A session that will be at the end of the talks. So I encourage everyone to take notes and jot down your questions during the talk so that we can return to them later. Okay, so I will now introduce our first speaker, Mr. Mike Willingham, who is the Director of Regulatory Affairs at Google Health, where he manages research and development teams using artificial intelligence and machine learning to assist in diagnosing cancer, predicting patient outcomes, preventing blindness, and much more. Mike is also an affiliate faculty member here at the School of Pharmacy at University of Washington, supporting the master's program in biomedical regulatory affairs. His talk is titled "The Application of Large Language Models and Generative AI for Healthcare, What are the Risks and How Can They Be Controlled?" Thank you, Mike. Thank you, Mike. We're very excited to have you. Please come on over. Thanks. Laser.
Okay, thank you. Thanks for having me today. I thought I would give you an introduction about large language models and generative AI, just in that it's obviously, even in the lay press, has become big news and evolving technology, and there's a lot of excitement. But with the theme of the symposium here around maybe risks and unanticipated side effects, I'll share what we've learned at Google in development of an LLM that's specifically trained in medical knowledge and encoded in medical knowledge. I will point out a couple of things. One, the information that I'm sharing is public. It's based on information that's in scientific journals and publicly available. I've included quite a few links in the presentation. So if those that want to dig into a little more detail later, that should be manageable. Also, I'm not really presenting on behalf of Google. This is basically my presentation on the topic and what's publicly available. We'll jump into, first I want to just give a high level overview of large language models and generative AI, because I'm not quite sure on what people's understanding and level of understanding on the technology is today. So I'll give a quick overview of that for some context. But the main part I'll focus on is the case study on a large language model that we've dubbed MedPalm, and I'll explain the origin of the name in a few minutes. Then looking forward, and understanding the basic capabilities of a technology like this, what are some of the obvious use cases in healthcare? And I can use that as a springboard to talk about the types of risks that we're seeing already with this technology, and at least some of the research and efforts we have around controlling those risks, and even setting standards and regulations for how these products will be managed in the healthcare setting moving forward. So let's first start with the baseline of artificial intelligence. In reality, in healthcare, AI has been applied for years in a lot of medical devices and medical technology in human-programmed logic and algorithms. Examples would be like 12-lead EKG interpretive monitors are human-programmed for interpreting EKGs, but effectively they're replicating an expert cardiologist in the classification of an arrhythmia. And then the middle category is more, I think, what has become more in lay terms of what people think of as, machine learning devices, where you're providing a curated data set to a computer, providing it with ingestion technology, and that it does pattern recognition, and you're training it to come up with classification or outputs that you expect. Most of these applications are fairly focused in what they do. Like, as an example, and was mentioned in my introduction, we have in some of the research that's been done at Google, we've looked at things like mammography exams, and we're able to ingest those images and provide risk-based scores on the images, and maybe even highlight regions of interest that a radiologist would want to pay attention to in their diagnosis. So that's an example of more supervised learning, where we're providing the machine with a curated data set, and typically that data is labeled by experts. So you can use that as a ground truth to measure the performance and output of the model. But then we move over to generative AI and LLM technology, and this is very different in terms of how these models are derived. They're based on deep learning neural network computing devices, and they're able to ingest huge amounts of information. I mean, it's sort of mind-boggling to consider the amount of information that these computers and models are intaking, and then they're performing literally billions of computations and establishing patterns. And effectively, the output now is you've got essentially an application that is conversing with you in your natural language. And that's actually in some ways you can look at it as that's the new programming language of an LLM. You provide it natural language English instructions, and it provides a response and output to you. So that's the emergence of this technology, and its capabilities are pretty astounding. I like to use this diagram. It's actually from a regulatory citation that I've worked with an international group, but it provides just some context in terms of kind of a Venn diagram of some of the terminology you see used in AI, with AI being the kind of the global coverage of this, and then with machine learning being a subset of that. And then the blue box is really what we're going to be talking about, is even within machine learning, what we would call deep learning, which is these layered neural network computing devices that these are based upon. Reinforcement learning is just, we'll get into that a little bit too. This is where you can, once you've got a baseline model to perform a particular type of task, you can also tune it effectively with some additional information, so it has even more particular expertise in a particular topic or task. So let's talk a little bit about the history of language models. There's actually been a lot of effort and development and publication on this, but it started with essentially computers learning the pattern of language and understanding the flow of language in any particular natural language. And the basic approach has been to develop what's known as tokens to assign to particular words. And once it starts to build a sequence of words, it develops a predictive probability on what the next logical word should be in that sentence or in that flow. And then, of course, that scales to sentences, paragraphs, etc. But that's the basic design, effectively, from a development perspective. So again, it's just looking at the next most logical word, and you can look at it almost as a calculating device. But the real breakthrough in the last few years started with actually the silicon, the computing devices underlying this technology. These are transformer processing units. I put a link down there and from Wikipedia that you can read if you want to understand the development. I wish I could explain the diagram on the left to you, but that's a little beyond my capability. But it's essentially a very unique architecture of neural network computing that allows for literally exponential speed increase in the ingestion of information for these learning models. And that was a huge breakthrough. It's pretty amazing when you look at the time frame. We'll talk about that too. These transformer computing units were developed, actually they were only really conceived in 2017. So you can point back to a paper that was written by a scientist at DeepMind, which is now a subsidiary of Google, but that proposed the design of these transformer models. And within now, 6 years, they've gone from concept to production to now mass production. And now they're scaling. Really, their capabilities are starting to scale like with typical Moore's law computing, like the speed and capacity of these transformer modules are increasing in their speed and capacity at that rate, exponential, literally doubling every few months now. So we're seeing just a tremendous increase in the capability of these models. And then let's talk a little bit about generative AI. I think most people are understanding, the concept of large language models, and you ask the computer a question, you get an answer, response back. But what they've started to sort out is we're not limited to text. We can provide learning of patterns through images, through sound, through anything that you want to provide it in any particular mode with the right context. And the unique thing about these models now is they're truly generative in that they can create net new content that didn't exist before. They're not basically just reciting information that they've learned. They're actually, with human instruction and natural language, able to create a new song or write code or write a paper, so that's a little bit of probably some of what you may have seen in the lay press about people worried about getting put out of jobs because these products can create, and we'll talk about that in a minute too, but they are amazingly capable. And today, in both text and code, they're ready for prime time today. You can actually have models that are available publicly today that are very capable in terms of writing authoritative papers. In my work, I do regulatory submissions, and there's a piece of work that's particularly time consuming called clinical evaluations, where we review enormous amounts of public information that are available in clinical data around a particular technology. We're looking for like risks or information that we need to make sure that whatever new product we're developing addresses what's known in that field. Typically, that takes a skilled senior clinical and regulatory person, maybe 5 to 6 months worth of time to really create a good body of work, and it's typically hundreds of pages. Last month, I was able, with a tool within Google, to create something that I would say is probably 95% complete and accurate within less than 5 minutes. And it was 130 pages worth of documentation. A lot for somebody to go through and proof, but the point is that saved a lot of work for somebody. So anyway, it's fairly impressive in terms of the capability. So you can imagine if you start, expanding that to other modalities, what the level of output could be. Just so you get a sense of kind of the emergence of this technology and where it is today, this is not about medical applications of LLM and Gen AI, but this is looking at it across all industries. This is from Sequoia Capital, which is one of the biggest capital venture firms in the country, or in the world, really. And this talks about like text, code, images, video, and across the timeline. So as you can see, in 2023, they're basically saying that text and code outputs available prime time today. It's on par with human capabilities. And within the next, 2 to 10 years, all of it will be at or exceeding what they would consider human capability. So let's jump into the case study. So now we've kind of given you a backdrop on what the underlying technology is. A scientist and a physician at Google a couple of years ago saw all this coming before a lot of people understood the capability, and decided to pursue kind of a moonshot project to develop a specific large language model encoded and tuned in medical knowledge. So they provided it with huge amounts of medical literature and knowledge. And so we'll talk a little bit about how we went through that development. But I put 3 links at the bottom there. The first one is essentially just a website that has a lot of reference and history. The other 2 are actual scientific publications that Google produced in Nature within the last year anyway. One was in December of 2022, and the other was in May of this year. And I'll talk about what those papers had to say. So first of all, the basis of MedPalm was based on PALM, which is Pathways Language Model. And this is literally, there's different ways to measure, but most people would agree this is the largest generic language model developed today. And again, it's based on these transformer technology. And this is actually the numbers that you're seeing here. The link I put in the bottom there, you could get more details on, but this is almost a year old. This was 2022. And at that point, it had 540 billion parameters and computations on the basis of all of this type of contextual information globally. So you can imagine today what it's capable of if you assume that that technology is essentially doubling in capacity about every 3 months. So figure out what the accelerated rate there is. So essentially on the right, the team built this MedPalm based on Palm, but then with certain prompting, which are the inputs that you can provide to the tool in natural language, and instruction tuning, which gives it essentially some training. Like this is how you would train a large language model to not answer a question that you would say is inappropriate. Let's say you have a generic large language model that you're going to make publicly available, like Chat GPT or Bard. If somebody asks, what's the best way to commit suicide? Or how do I build a bomb? You would imagine you probably don't want the tool to provide an answer to that in public, right? And so you provide instruction tuning that gives it some guardrails about what it will and will not answer. And then even within that, then you do instruction prompt tuning, which is a combination, so that even instructions that a user might input, you'll flag ahead of time to say, give them a hint that that's not a topic that we're going to entertain, right? So anyway, this is how you take a huge, large, learning model and language model, and then focus it on a particular area of expertise. The other thing on the left that we had to consider was, how do you provide a benchmark for measuring the accuracy of the output? I mean, the outputs are innumerable. So how do you test and validate that the tool is performing at an adequate level for release to the public or for specific types of professional use, et cetera? So what the team did was they started with a number of different tests and bodies of medical questions. And on the left or on the right top, you'll see MedQA, which is the United States Medical Licensing Exam. So you have a huge body of very complex medical questions that are used to license medical students. And so that's an example. And they have others that from across the globe. So this is a fairly global set of medical question and answer that they used for not tuning the machine, but measuring how it performs in the output. So, and to just give you a sense of the types of questions, they go all the way from very simple and direct questions like how serious is atrial fibrillation to very nuanced, contextual, situational questions that require, thinking literally and then provide perhaps 4 or 5 potentially legitimate answers and ask it which one's the most likely or the most appropriate. So very broad spectrum of complexity of question and answer that they developed. So I mentioned the 2 papers that were released in Nature magazine. And the first was December 2022, which was the evaluation of the original version of MedPalm, called MedPalm 1. And it was the very first large language model in publication that exceeded the benchmark for passing the medical licensing exam in the US. So effectively, the tool in its first version was able to achieve a 67.5% pass rate in medical licensing exam questions. And the bars on the left were other publications of similar large language models that had attempted to do the same thing. So then the team took that performance and asked themselves, okay, how do we take it to the next level? How do we improve the product and the large language model from there? And they developed a new version in 3 months' time. And within 2 more months, they published a brand new publication with some additional insight and information. And when it was put against the medical licensing exam, again, a different set of questions, but from the same data set, it achieved an 85% pass rate, which historically, students that achieve 85%, they're in the top 20 percentile of medical license students. So, and that was just in essentially a 5-month period from end to end. So that, again, gives you a sense for how fast this technology is moving. And this is an example of one of the questions and answers that MedPalm 1 provided. And the team brought in a number of clinicians, these are not medical students, these are internal medicine and primary care doctors that provided their answer to these questions. And as you can see, while the answer that MedPalm 1 gave was technically accurate, it did omit some contextual information that would be important for a physician or a patient to have. And so the team developed a bit of an algorithm, like a dozen different parameters for human clinicians to judge the answers of MedPalm and look at what it met, what it didn't meet. In this case, they identified that it omitted certain information. This feedback was used to tune the MedPalm 2. And then this is the same question, but the answer with MedPalm 2, which you see is more comprehensive and met all of the identified criteria. So impressive, but if I really want to use this in real world, and that's a medical, here's how I would ask the question. If you had a medical student who just passed a licensing exam, would you trust them to, provide medical care, or do you think there's more to it? So the point really being is, while this is extremely capable, there's still definitely some gaps and things and risks that we need to assess. And so if you look at where it is today, and I'll talk about these in more detail, but LLMs encode implicit knowledge bases. And so they can be somewhat simplistic at times in their logic. And they're known to have hallucinations, which I'll explain in a minute. And they also amplify biases. I mean, all of our information today, our own language, includes bias. And so it's going to be a reflection of human communication and language. But that doesn't mean we can't do better, right? And be knowledgeable and vigilant about that and see what we can do to improve that. The second is really, how do we measure, how do we benchmark the performance of these? And, the example I gave was just that. It's an example. It's not like it's a community relevant benchmark that's been validated by the medical community. That was Google's proposal at this stage and for demonstration purposes, but there's still a lot of work as a healthcare community to get our arms around how would you actually agree to measure the performance of these applications. There is a big bench is actually a kind of a federated learning community for LLMs and AI in general. It's not medically specific, but it would be a good example where lots of different constituents and stakeholders worldwide could contribute to that effort, right, to develop a benchmark for how we would control these. And then the key also is like metrics. How do you actually measure the output and accuracy of a product like this, which is very important depending on how you would apply it to healthcare cases. So if you look at what are the likely use cases in healthcare, I've got a few bullets. I mean, the list is huge, and we could talk about health economics and outcomes. There's a lot of data analysis that these tools could provide insights to. But there are some low-hanging fruit where I think you can use these tools to help summarize clinical information, to retrieve data from huge, vast, complex data systems and hospitals. You can use it for educational purposes. And some of like those first three are good examples where it's not really in the direct line of patient care, so the risks of error are not as great, let's put it that way. But you start to apply it to actual clinical decision support alongside a physician, or even providing like a medical assistant as like a chat bot to work up patient condition before handing off to a physician, or even like therapy planning. You've got a patient with multiple comorbidities and you provide the tool with all these inputs and it suggests a therapy plan, right? So you've got that whole spectrum. But when you get down into those lower stages where you're directly in the path of care, then the risk obviously goes up and the level of performance has to be as best as we can make it, right? So how do we go about that? And the one thing I would say is you are going to see a lot of people applying this technology to healthcare. This is just a recent article this week, actually, or last Friday, on projections from some of these, market firms looking at how much investment they think is going to go into this space with generative AI. So let's talk about some of the risks. I mentioned hallucinations. The 4 bullets on this page, I would say, are either unique to LLM and Gen AI technology, or they're certainly exacerbated. They're greater for this type of technology. So the first one, hallucinations, is this behavior with LLMs. If you ever interacted with like ChatGPT or these, they can, the answer you get back from your question can sound very authoritative. And if you're not an expert in whatever the question was that you asked, you might not be able to tell if the information is patently wrong. And that's in a nutshell what hallucination is. And it's very common. I mean, some of these models, even like MedPalm, we can find examples of hallucination where it's clearly wrong. And so there are some techniques that are being developed with how we would test for that and how you tune with reinforcement tuning the models to reduce that. But nobody's figured out a way to eliminate it. So it's one thing you have to deal with. The next 3 are really kind of like the analogy I use is like security engineering, where we're concerned about malicious actors, like people with malicious intent could use these tools for harm. And you have to be realistic about that. And how would we know that that's happening? How would we make it impossible or difficult for people to use that? Obviously misinformation, disinformation, we hear about all the time if you ever pay attention to US politics, but deep fakes is another category where you've got, particularly with like audio or video, that absolutely looks realistic, that you're assigning outputs to some human that never said or did those things, but yet it looks real, right? To propagate whatever belief they want. And then data poisoning is the front end, where you can actually provide input and tuning to the LLMs to redirect their logic and concepts. So those are all things that we're working on trying to mitigate. The rest of these are more common with other AI tools, with biased information, privacy concerns, ethical and legal considerations. Like in the case of these LLMs, if somebody decides to take a product that was developed by one of the tech companies but apply it to healthcare, who's responsible for if there's a problem with that? Is it the user, or is it the company never, or the developers or researchers never claimed it would be used for this purpose? So there's a lot of ethical and legal regulatory considerations. And then the last one is just sort of a highlight that these transformer computing devices I mentioned are kind of like blockchain technology. They require huge amounts of energy to run the computational engines around these things. So they're very energy consumptive technology. So the things that we're doing that we're suggesting that you follow in development of these models in healthcare particularly are around rigorous evaluation methods in the development of these products. And a lot of it is nuanced and in context. You have to also, to fight bias, you want diverse inputs and demographics involved to make sure you're covering that. And then, obviously maybe limited releases of these products in pilot groups where you get tight feedback would be very helpful. And then launch these with very robust controls in place, providing guidelines to the users. You can use good data governance techniques to make sure that the information within these models and what they touch are controlled and not available publicly. Invest in cybersecurity tools, and there's also a whole field being developed around quality analysts for this type of technology, people that would actively monitor performance and identify issues that need to be addressed. And then I put in just some current methods that are being used to deal specifically with this category of hallucinations. And you'll see some of this if you go back to the papers that I cited that would be available, so you could look at some of the details that are available there. And then I'll just leave you with this last comment that was the CEO at Google, we celebrated our 25th anniversary a couple of weeks ago, and he was reflecting on his 20 years at Google and talking about this technology and all the other pretty amazing things that have been created through the last 20 years. And he said, this is one that seems amazing, but more than likely, if it follows typical technology, it'll become fairly ordinary in the not too distant future. And I think that's probably how you'll see it emerge over the next few years. So thank you.
Thank you, Mike. Thanks, Mike. That was great. We have time for a couple of questions if there's any quick questions. Teddy, go ahead.
What's good enough? So doctors today, we get second opinions. Doctors great safety that are wrong. And the second opinion identifies that. So really, what's good enough? What do we expect the models to be able to do? When will we be satisfied, if ever?
Actually, Teddy, maybe repeat your question. So, because I know we've got a lot of listeners online to make.
Sure. So the question was, what's really good enough with these models? Recognizing that even in clinical practice today, with doctors who practice for a long time, we recognize that sometimes a second opinion is necessary, because that first doctor may be wrong, or they may just have a different background that doesn't give, adequate justification for their answers, but they're always confident as is ChatGPT 4, right? So when will we be in a place that we feel good about?
Yeah, no, that's a great question. And it is one of the big challenges here. And I mentioned that was sort of what I was talking about in benchmarking, right? It's one of the very first things when we're working with healthcare organizations to figure out how to apply this. The first thing we explore is what is actually the use case. Let's really talk about how you want to apply it, see how much structure we can put around that. And then the very next question is, how do we measure whether it's successful? What is ground truth here? How would we compare that to? And in almost all cases, this is artificial intelligence. So we're mimicking human behavior. So typically it's going to involve a panel of experts in that particular topic to judge the output of the application to determine, but you need to plan that up front, right? You need to, and that we spend a lot of time going through some deep discussions about planning all of that before we even start our work in some of these, but it's a great point. More question? Oh, we got, sorry.
Hi. So you talked about the risks of LLM and Gen AI, the benefits, risks, and the ethical concerns. Are there any regulatory challenges with these?
Oh, yes. Yeah, I think all of the regulators around the world are concerned and reaching out. There's actually a lot of work being done in the standards world to try to create some guidelines and standards around the development of these kind of tools. And there's actually a large conference that's Xavier University is sponsored every year. It actually meets next month in Cincinnati, where a lot of people globally come together along with regulators and it's focused in health AI. So yeah, but it's very much emerging. So if I'm back next year and you ask me, it'll be a very different answer. Let's put it that way.
Thank you.
Thanks, Mike. I think we'll move on to the next speaker, and these are great questions. So let's save some of these for the Q&A at the end as well. Our next speaker is Dr. Noemi Krief, who is a Senior Research Fellow at the Center for Health Economics at the University of York. Her research is centered around incorporating methodological innovations from statistics, causal inference, and machine learning into health economics and health policy research. We're excited to have Dr. Krief joining us all the way from York. Her presentation is titled Machine Learning to Answer Causal Questions, How to Avoid Misleading Interpretation. That I will turn it over to you, Noemi.
Thank you, Esther. And thanks for having me. It's a great honor. I gave my talk a very ambitious title. I hope I can bring some ideas around how to avoid misleading interpretation. I don't think I can answer all the questions and solve all the problems in the next 25 minutes. So how does this work? Okay, so the premise of my talk is that As researchers working in the space of health economics, public health, medical research in general, we often want to answer questions which are of causal nature. This can be fairly simple questions, asking about the average expected impact of introducing a new policy, or perhaps the average ex-post impact of a policy which already has been rolled out. And it can be something more ambitious, such as questions going towards personalized medicine, which treatments should be given to which patients based on their characteristics, which we can measure, potentially including detailed characteristics such as genetic information. And what I will try to talk about here is whether machine learning can help address some of these questions. And a very quick preview of my talk is, the answer is yes, but. Yes, but only if we apply these methods in very careful, specific, customized ways. And even if you do that, there are many potential pitfalls, challenges, which we need to pay attention to. And I picked 3 particular ones. There are more, and I won't be able to cover even all the nuances of all of these, but let's try. So causality, explainability, and uncertainty are the 3 areas I would like to talk about. And Asta, if I run out of time and I only manage to talk about causality, that's fine, because I think that's the most important. I was told to bring examples when things can go wrong. And that's a bit scary, because if I bring examples from other people's published work when things go wrong, that's kind of disrespectful. And if I bring examples from my own research and things can go wrong, that's kind of, really making me very vulnerable and potentially making me look like not a very good researcher. So I have a combination of published examples, made up examples, and examples from my own ongoing research where, things got a little challenging, and I may not even have the final answers there. So let's see. So the first area I would like to cover is the age-old mantra: correlation is not equal causation. Hopefully, some of you like XKCD and this particular comic. It's always good to remind ourselves. In particular, in the space of machine learning. So after Mike's talk, it's important to bring us back from the future to the present and perhaps the pre-2012 times. So here I'm going to mostly talk about supervised learning, when the aim is to take a bunch of predictors, perhaps at the patient level, perhaps very detailed characteristics of medical information, socio-demographic information, churn these through some algorithm, which can be our old friend logistic regression or something much fancier like neural networks, and get some predicted outcome which we care about. And this can be something like a probability of death from a given disease, probability of readmission to hospital, or perhaps predicted healthcare costs. The great strength of supervised machine learning, and this is the reason why statisticians, economists got really excited about it in the last 10 years or so, is that we can build models and then we can evaluate them. We can actually learn which model is better than the other by simply looking at their performance, in particular, looking at their performance on out-of-sample predictions. So on people which I haven't seen, when I'm fitting my model, do I manage to predict these events correctly? And if I don't manage to predict them correctly, then that's wrong. That's a bad model, and we need to find something better. Another objective of such supervised machine learning is to learn something about the relative importance of these predictors in the outcome. What I would like to claim that these models off the shelf, as they have been proposed in the 1980s, cannot do is to understand the causal relationship between these predictors and the predicted outcome. And a very kind of silly example which I brought for you is imagine we have some cool model which can look at pictures. So images, Judy's talk will touch upon such cool models. And on some pictures we have some pieces of clothing or shoes or umbrellas which we wear when it's raining. And we want to use these pictures to predict whether on a given image there is rain or no rain. And I expect that a good neural network will be able to pick up these as important predictors of rain. And it's fairly clear that even though these are important predictors, this relationship is not causal in this direction. It's in fact causal in the other way. And this sounds very silly, but if we start thinking about these predictors from an area of medicine and health economics, then we can get into real trouble if we start interpreting things causally. And the first example which I brought is a paper which I found while preparing for this talk. This is a 1997 paper, which is very nicely and clearly written. I really liked it. It builds a prediction model for inpatient pneumonia mortality. And compares a bunch of machine learning methods, including neural networks. So the authors are pretty transparent about the fact that results from this model will only be useful for decision making under very, very strong assumptions. And the particular assumption they highlight is that if their model is going to predict a low probability of death in hospital for a given patient, then that same patient would also have a very low probability of death if treated at home. And in that case, then it's fine not to admit them to hospital. They are low risk, they can stay at home. I think we can very easily come up with many reasons why this assumption may not hold. At home, there are no health professionals. There may not even be family members who can look after patients. So that's the first reason why we maybe shouldn't use algorithms like this to help decision-making straight away. Another reason is a surprising finding, which kind of came out of this paper. So the authors found a lower mortality among patients who were admitted with asthma. And well, if we use this again at face value, then we would maybe not admit those patients. They might be fine at home anyway, these asthma patients. So now the reason for that was that these patients were actually triaged quicker, they got better care, and that is why they were not dying so much. So I think this paper is old, but very nice, very clear, and nothing really changed in the last 20 or so years, which would make us think that supervised machine learning methods can help us with medical decision making without making extra assumptions and without very carefully thinking about the interpretation. Now comes my made-up example to dig a little bit deeper into this. So the question I'm posing here is, could prediction models tell us about the expected effect of intervening on a given risk factor on the risk of something such as a cardiovascular disease? So it would be really nice if we could somehow use predictive risk models to tell something about what would happen if for a given patient, their BMI would be reduced, their physical activity would increase, or they stopped smoking. And well, turns out that even before machine learning, there were plenty of predictive risk models, risk prediction models developed. For example, the famous framing and risk equations are trying to give us a 10-year risk of coronary heart disease, and it looks like this. There are some numbers in there, there are functional forms, logarithm, and so forth. And essentially improvements on these traditional risk prediction models. With machine learning, they don't have these numbers anymore. We don't necessarily have these interpretable functional forms. I will talk more about later about that. And the output is something like this. We learn about the relative importance of each predictor in the final risk score. So for example, from here, we learn that cholesterol levels are very important. Question to the audience to make this a bit more interactive is, which one do you think oh my God, I really ruined this. Which one do you think is more useful to learn about intervening on a risk factor? And I wanted to ask to raise your hands if you think the first one or second one. Anyway, in the matter of time, I guess I managed to reveal this, that I think, and I hope I'm right about this, it's neither of them. Without further assumptions, we cannot really make such causal claims. And why is that? It's because the risk factors are not randomly distributed in a population. In fact, they influence each other in very complex ways. And the prediction algorithms, which are developed for predicting such risk scores, they don't tend to rely on a causal model which can take into account this complexity. So what do we do if we do want to answer a causal questions, if we want to learn what would happen to a patient if they stop smoking? Well, then we have to go to the world of causal inference, and we have to start thinking about somewhat esoteric concepts such as so-called counterfactuals or potential outcomes. We need to imagine every individual in two states of the world, if they are still smoking and if they stop smoking. And we have to kind of keep this in mind throughout. I guess we all know that we live in a single world as far as we know. So we can only observe every individual in one of these two states, which tells us already something about how machine learning cannot fully work here, because the usual tools of model validation cannot work in a data set where we only have half of the relevant observations because the other one is missing. Of course, if we have a lucky situation of having a randomized trial, which for pharmaceuticals, for some medical devices, even for some public health interventions we might have, then that's great, because we can simply compare the outcomes of a treated and control group if they were randomized, and we can actually learn something about, on average, what would be the impact of the intervention. However, for many, many situations in health research, we will not have this randomization. If we are thinking about smoking, we definitely cannot randomize people to smoke or not. So we need to think in terms of a causal model. And very importantly, we need to think about this concept of confounding. Essentially, we need to adjust for variables which influence both the exposure of interest, smoking in our case, and the outcome. How is this normally done? Well, if we have data, then we can perhaps build a simple model where we are modeling the outcome as a function of the confounders and as a function of the exposure and maybe noise. And essentially, we could estimate the impact of smoking by just doing that. The question is, but this model is quite simple and linear, and we all heard that machine learning can do lots of things for us in an automated way. It could perhaps find a better, more flexible, bigger model. So would this simple linear model be improved by machine learning? I guess maybe now we can put your hands up if you think so. Do you agree that we could use machine learning to improve on this model and trying to estimate the positive effect of smoking? People are very, very doubtful, and I do I do appreciate that, because on the next slides I'm actually going to show you how first the things which machine learning cannot help in this situation. For example, machine learning won't be able to tell us anything about confounders which we might leave out. For example, there is a physical activity which may not be measured in a patient records, but it influences both smoking and cardiovascular risk. If we have some omitted variables like that, this model will not be appropriate. Other things machine learning cannot do is it cannot tell us about variables which we should not be adjusting for. For example, we shouldn't be adjusting for mediators because it would sort of adjust away some of the useful effect of the, well, in this case, some of the harmful effect of the exposure. And similarly, we shouldn't adjust for colliders because that's, yeah, there should be an arrow there. You shouldn't adjust for colliders because that's also post-treatment variable which could bias your estimates. So there are a whole bunch of things which machine learning cannot help us with here, even though if we have a large number of potential covariates to adjust for, the researcher trying to do causal inference have to make some very hard choices, some very careful assessment before starting to do estimation. But the good news is, and this is where I would turn more optimistic, that once this is done, so once we convinced ourselves that we can measure all the confounders which influence smoking and influence the outcome of interest, and this might be very hard, and this might be actually impossible, then we can carry on and actually use supervised learning appropriately to help us with our causal inference. What can we do here? we can use the power of supervised learning to essentially build a better version of this, now assuming that all the choices were made appropriately. So what can a better model do? It can capture nonlinear relationships between the covariates, confounders, and the outcome, between the treatment and the outcome. It can capture interactions among the covariates. And if we have a really large set of potential confounders, for example, we have some genetic information and that comes hundreds and hundreds of variables, then we can do some selection amongst them using appropriate machine learning techniques. The state of the art for using causal machine learning for estimating treatment effects is essentially, well, it's better to use two models than one. So ideally, we model both the outcome and the treatment mechanism. And in practice, the reason for that is, again, the old famous quote by George Box, that really all models are wrong, but some are useful. So by using machine learning, it's more likely that we get to use full models than by using a pre-specified simple linear model. But they will still be a little bit wrong. So it's best to combine two a little bit wrong models than one. There is some pretty exciting statistical and econometric theory which can describe this much better. And the methods, if you want to explore this space, then the methods to look for from biostats and economics include targeted learning, double machine learning, and so forth. The promise of these methods is that by using a good machine learning method for the statistical model specification, there can be less bias in the parameter of interest, which is the average causal effect, than what we would get if we would use a simple model, which happens to be misspecified. For example, linearity wouldn't hold. Okay, so there is a second area where machine learning is being used for causal inference, and it's very fast growing, and some of my research is using these methods. So my examples will be around here. Is then we want to use machine learning to help us uncover heterogeneity in treatment effects. So here the idea is that we could do something like supervised learning. We could try to build a prediction algorithm which takes individual characteristics, but instead of trying to predict the outcome, we could try to predict both of these potential outcomes, which I showed you before. So we can try to predict both what would happen to someone if they get the treatment and what would happen to the same person if they get the control. And if we can do this, we can essentially calculate the so-called individualized treatment effect for this particular, for every single patient. There are lots of nuances here, which we can talk about later. These treatment effects are really only individual to the extent that this information we are capturing is rich enough. There will be lots of things which may not be captured, so it's not really fully individualized. And again, those who want to look for these methods and use them in their research need to look both in biostats and economics again, and need to look for things like conditional average treatment effects, causal forests, double robust learners, dynamic treatment regimes, and so forth. What I would note two things. One is that a huge difference between supervised learning and doing this, which is increasingly called causal machine learning, is that we can never fully validate these models because these potential outcomes will be half missing. We will never be able to use the usual model validation tools to tell us whether a model is correct or not. And that's a giant challenge. So what we need to do is we need to go back and be very, very careful about setting up a causal model, thinking about our assumptions. And only after that is done, then we can put on a second layer of estimation, and then we can throw machine learning algorithms at it. But that first step has to be done the hard way. Okay, so I'm going to, how much time I have? Excellent. So I'm going to now come to the scary moment that I'm going to show two examples from my own research, which is actually trying to estimate such individualized or heterogeneous treatment effects. And through through that, I'm going to hopefully illustrate two more issues, explainability and uncertainty. By the way, I was trying to generate images by DALL-E for these slides, but then it kind of threw me out. It told me that it's just, your request is taking too long, you should go away. So I ended up choosing non-copyrighted pictures of famous dead painters. For example, this girl looking at something which she doesn't quite understand what it is, but if you look carefully, then it's a moon and birds on this painting. Okay, so those doing traditional statistics, they potentially use data. They are used to having a nice kind of output of estimated coefficients and p-values, and you know, we can interpret the marginal effect of some covariate on the outcome of interest. With machine learning prediction models, typically we don't have anything like this, and that sort of hurts those researchers who are used to this, and they're used to like kind of understanding what's going on. So I'm going to show one example of my research when we faced a little bit of a challenge by not getting this. So very, very quickly, I have a few papers which are looking at the impacts of a particular expansion of subsidized health insurance in Indonesia on a few outcomes. Here, I'm going to talk about infant mortality. So the idea was to employ a few causal machine learning methods to estimate individualized impacts of the policy, and then do something with these estimates to try to inform an optimal allocation of the policy. So the output from a causal machine learning model is something like this. So what we get is a histogram of predicted treatment effects for every mother in our sample, and then we kind of stare at it and try to see what's going on here. So this is infant mortality. So we would like to see negative effects. We would like to see reductions of infant mortality from having health insurance versus not, and we see that mostly, but we do see a chunk of the sample here where the estimated effects are actually positive. So it seems that some people were in fact harmed by having health insurance. How can we make this interpretable, and how can we get something like this, which actually tells us a story? It turns out that we can actually go back to our friend, the interpretable linear model, and we can have one more layer of analysis. We can put these estimated treatment effects in regression, put it on the left-hand side, and regress or covariates on it, and in fact get some output. And from this output, what we learn is that most variables in our data, this is a bunch of socioeconomic covariates, rurality, participating in social cash transfer programs, and so forth. So mostly they don't seem to have an impact on the treatment effects. We see that from confidence intervals crossing the zero. So mostly, it seems that most of our covariates are not actually explaining this heterogeneity. We do find two groups of covariates which do. So it seems that women who are older at childbirth and who receive cash transfer, they seem to benefit more. And then we find something somewhat concerning, that those with the so-called poor card, which is a certification of status of poverty, they benefit less. In fact, they seem to be harmed. And so we were really worried about this result. We did one more thing to kind of figure out what's going on. And what we did is that instead of a linear model, we chose another interpretable algorithm which could shed light on what's going on, a so-called policy tree, a decision tree, which gives us recommendations on who to provide subsidized health insurance in order to maximize benefits within the population. And once again, we do find these confusing results. So the recommendation is that those who are in the lower three wealth quintiles and they have this poor card, they should not get the health insurance. So, okay. So what is going on here? Well, there can be three potential explanations. One is the effect is real. There is a particular subgroup, particular vulnerable subgroup of the population who are actually better off not being insured or not. There can be some reasons why this might hold, but we don't really believe that. A second explanation can be that some of our causal assumptions are violated. So in this subgroup, somehow there are some unmeasured confounders which we didn't take into account. And the third explanation is that maybe this data is just bad. Maybe this variable does not measure poverty and socioeconomic status correctly. And in fact, I talked to our Indonesian collaborators just 2 days ago about this, and they still don't know which one is going on. And they are leaning towards the bad data. So this is, again, this is me being honest about sometimes we just don't know the answer. What we could have done in our paper, we could have just deleted this variable and just presented the result without it. But we want, because this is a methods paper, we actually wanted to highlight that doing this interpretable analysis, either by having something like this or having something like this, actually tells us something about what the recommendations of the algorithms are based on, instead of just giving a yes or no answer. Then the last thing, which I have maybe 5 minutes to talk about, is around uncertainty. So uncertainty is a huge topic, and I think in HEOR, people mean many different things about it, and I only have a few minutes, so I can only talk about one aspect, and that aspect is around estimation of uncertainty due to the uncertainty in sampling. So when we do research and we get some estimates, then we typically want to be able to say something about how confident we are in those estimates. And one way of doing that is to record 95% confidence intervals around estimates. Remember my histogram of health insurance impacts. It would be very nice to have confidence intervals around each of those estimates in my histogram. Now, turns out that it's actually not very easy to do that when we use supervised machine learning methods for generating these predictions. And one reason for that is traditionally this was not really the main focus. Supervised machine learning prediction algorithms were not developed to test hypotheses. While hypothesis testing is pretty important in economics, econometrics, traditional statistics. So with my colleagues from York, we actually did a scoping review to check whether the causal machine learning methods, which are aiming to get these individualized treatment effects, fare any better? Can they provide estimates of uncertainty? And we found that sometimes yes, but mostly not. And there are some methods out there, for example, Bayesian versions of machine learning algorithms, which actually can quantify some sampling uncertainty. So in another study, which we did with colleagues from York, we used these methods. In this paper, we tried to uncover heterogeneity in the impacts of hypertension targeting intervention, and big relief, we were using trial data. So we didn't have to worry about confounding. Still, within this trial data, we wanted to know which are the patients who would benefit more or less from getting this intensive hypertension targeting intervention. And what we actually were doing is we were trying to get counterfactual survival curves for every individual, get a survival curve which describes how their survival would go if they get the control, and how their survival would go if they get the treated, and where treatment is intensive and control is the standard hypertension control. We wanted to have some measure of uncertainty because we wanted to use these survival curves as inputs in a decision model later. So we chose to use Bayesian additive regression trees to model survival. And because the model is Bayesian, we get a posterior distribution of four estimates. So for each individual, we actually managed to come up with uncertainty around their estimates. So for example, for this particular individual, we can see while in their point estimate, it seems that the standard treatment is better than the intensive. The ranges of uncertainty are really overlap. We ended up not, so the objective of this study was not to look at every single patient and say, well, it worked for this guy, next, it worked for that guy, but to churn this through a decision model and get something about the population out. And if I have a minute later, I can show you the result of that. But yeah, so the lesson from this is that it is not too many causal machine learning methods currently which can do this quantification of uncertainty, and depending on our objectives, we might want to look for those which can do it. So I have a summary slide. The three things I guess I want to try to say today. First one is machine learning prediction models are typically not informative on their own of causal effects, and because of that, on their own, they should be very carefully used to inform treatment recommendations. Causal machine learning can enhance both observational studies and RCTs by improving model specification and producing more nuanced evidence. However, we still need to take care and tread very carefully. Study design is crucial. There are several assumptions which will never be testable, and we cannot use the usual machine learning validation tools to do that. Ideally, we want to look for tools that allow for explainability in order to understand what's going on in our data. And if we need to select methods which can quantify uncertainty around estimates. I do realize there are lots of further important considerations which we could talk about, and perhaps we can do that during the discussion. I haven't talked at all about the practical, ethical, and fairness implications of recommendations from any algorithm, may that be supervised machine learning or causal machine learning. And I'm not an expert on those, but I'm very happy to hear the views of those who might have some ideas here. And for those who want to learn and use these methods, I have some weekend reading and, in fact, a much longer reference list if someone is interested. Thank you so much. No extra content for today. Thank you.
Okay, great. Thank you, Noemi. That was great. Again, if there's any quick clarifying questions, we have a couple of minutes for those. I'll ask that you save more substantive questions that could enrich the conversation later in the Q&A sessions for the end. So any quick clarifying questions about Noemi's presentation, please raise your hand and we'll bring the microphone over.
I'm not sure if this is a quick clarifying question, but I was just trying to understand the limitations of using different data sets in these models. And from your penultimate slides, it seemed like using randomized trial data is most effective. So I just wanted to understand if that's the correct interpretation of that, or it's much more nuanced than that.
I think it's a good interpretation. There is all this, I mean, I spent a lot of time looking through these causal diagrams to sort of signify that this is something one has to spend a lot of time when designing a causal study that uses observational data. And if you have a randomized exposure here, then you can skip this. You still have to pay attention a little bit. For example, I give you one example. You can still have a mediator of a randomized exposure, and then if you put that in your statistical model, then you still might, you still have to be careful, but you don't have to worry about confounding, and that is a huge benefit. Having said that, you don't always have randomized trial data, and sometimes we want to learn something about the word, even if it won't leave the perfect answers. So.
Any other questions? Okay, Not. Our final speaker is Dr. Gichoya, who will be joining us virtually. So please give us a few minutes to set up. And in the meantime, please help yourselves to some coffee or tea outside. And let's reconvene at 3:25 in 5 minutes. Welcome back, everyone. All right, so last but not least, we have Dr. Judy Gichoya, who is an associate professor at Emory University and works in interventional radiology and informatics. Her career focus is on validating machine learning models for health in real clinical settings, exploring explainability, fairness, and a specific focus on how algorithms fail. Dr. Gichoya will focus on the application of AI to imaging in a talk titled Hidden in Plain Sight, Harnessing AI's Ability for Population Health from Medical Images. And with that, I will turn it over to you, Judy. Thank you.
Thank you so much for the invitation and also flexibility to allow me to participate remotely. And here are my disclosures and nothing that's going to be conflicting or biasing the talk. So I hope everyone can hear me okay. So, when we look at imaging, the trend has been growing, and this is, obviously for, health policy and the big dollars is of concern, but the reality is that imaging has been exploding. But more so, we find that that we see that there is quite a lot of reduced radiation. So if you look at the last 3 years through COVID, many patients have moved to telemedicine. And, in the past, you'd have to bill, you have to bill and say, this was my physical examination. But in a teleworld, scenario, you pretty much cannot do a thorough physical examination. And even if you look at the changes that are happening in the emergency room, where the patients get imaging even before they're seen by the doctor because of the triad systems, then imaging plays a big role. The reason why I'm showing you this, those are just the factors that have made imaging explode. It's really that when you present to the emergency room with a chest pain or something like that, it's very different from what you end up with. And so what we can learn and take away from this is that there's an opportunity for us to use imaging for what is called opportunistic screening. And so in my talk, I'm going to show you some of the AI use cases, and then bring my work is around bias and equity and health equity. So I'll bring, tie in why this is important for this. And then also on the other end, end up describing some of the shortcuts that can occur in terms of understanding how these images work and what their impact is when you think about population health and larger, broader community outcomes. So my first question is, are image-only models better? And I'll show you some examples. It's October, so I hope that you, if you're female, and your mom, your sisters, your daughter, are encouraging yourself, if you're eligible, to get breast cancer screening. And Nancy's, unfortunately, she's passed on, was someone who was very faithful to getting her annual mammograms. And these are pictures when you get the screening mammogram. So screening is a core public health function. And, if you have this type of breast here, it's very dense, it's very difficult to see through breast cancer. And so for a disease where we've seen quite a lot of improvement in terms of outcomes, in terms of treatment, we still see some Black and Hispanic patients still suffer early deaths, more aggressive cancers, and late diagnosis. And so this understanding of risk remains still a big dilemma, despite the downstream successes that have been achieved in this field. And so this is one of the models, one of the many models that have said, look, we can tell you the risk of breast cancer. And even if I've used some red boxes, it doesn't tell you where the cancer is going to come, but it tells you your 1 year, 3 and 5 year risk. But more importantly, it takes these 4 images of the breast, transfers them to zeros and ones, extracts them, and aggregates that value here. And if you have clinical factors, for example, family history of breast cancer or another cancer, for example, ovarian, then you can input that, but otherwise it can give you, sort of your risk of breast cancer. Then what's important is that to look at the performance of this model in the context of these 4 other models. These are, the clinical models that are used today. They're not very good. You need to know a lot of history. For example, the teracruzic, I may not even know some of these factors, but yet the Mirai model can use the image only or combination of clinical factors. And when you look at the performance, when it's in this case, the metric is AUC, you find that it actually performs better than the existing clinical system. And so raising a question, can image-only models be used for screening examinations? And this is something that we need to figure out and understand how, what's the impact of this. A similar case is actually breast arterial calcification. So you get your screening mammogram, it tells you have cancer or no cancer, it really doesn't tell you the risk of breast cancer. But, you can imagine cardiac health is something that is not well understood. Women tend to be actually ignored. There's quite a lot of unconscious bias. They're rarely referred for advanced imaging and interventions. And yet 40 million women receive screening mammograms every year. And there's prevalence of calcium, of arterial calcifications on breast, but we don't understand what do they mean. But deep learning allows us to quantify some of these calcifications. We did some of this work where we looked at some of the annotations. It turns out now that people are understanding that it's not just the presence of calcium. When you think about coronary calcifications seen on CT scans, and these images require quite a lot of annotations to get. But the deep learning model actually works okay to tell you, hey, this is the type of calcification. These are several architectures. It doesn't really matter what you choose. And, for this segmentation task, we use the Jacquard score. And here is some examples where you can see different types of calcifications. And we drew some of them. These are just in the arterial systems. And then we start to stitch them together and come up with sort of like a calcium score for the patient. And you can see that you can apply it longitudinally if this is a patient whose calcifications are increasing. But what we don't know is really what the significance is. So for example, you see breast arterial calcifications can be a marker of calcifications for chronic kidney disease. So that's one of the things. But when we look at it from coronary artery calcifications, it's still something that it doesn't predict the coronary artery calcification, although there's current work that is trying to see what's the significance for atherosclerotic cardiovascular outcomes and cardiovascular disease. So another test that is done not specifically to look at calcium, but it's, is acquired on 40 million women who are most likely going to be underdiagnosed when it comes to their heart disease or, cardiac disease, not just hearts, even stroke. But again, deep learning providing us an opportunity to look at the calcifications. So when it comes to, as people who are involved in healthcare economics, this is a great paper. I hope some of you have read it. And if you haven't, you're going to look at it. This work by Ziad looks at a managed care algorithm. And what this does, it says, calculates a risk score and says, well, this patient is high risk of bouncing back, in the hospital. So we should provide them more resources. They can become home resources, more, just assistance to make sure that you're not always coming back to the hospital. And it has sort of like a cutoff point where you get defaulted into the program, but it really relies on understanding your illness severity. Unfortunately, the algorithm uses the healthcare cost. Now, it turns out that Black and white patients in healthcare cost very differently. Black patients tend to go to the emergency room. And even if this model was never trained with the racial information, it used a metric, a proxy. And this is going to be one of my call to actions from you, is to think about what are some of these proxies and what they encode. And it turns out that it learned that, for Black patients, the time they're being referred, they have more active conditions at the risk score. And it's because it's, the white patients tend to go to the primary care doctors and they end up spending more, but they tend to be a little healthier at the risk score. And by changing just the outcome metric, this was improved the number of patients who were, this is the simulated number of eligible patients who would be referred for care. And so again, showing you, first of all, two things from this work, that it's very difficult when we use ICD codes or some of these disease markers in the EMR to use them for a downstream policy effect or change, but also that the metric when it comes to deep learning is super important, else you can actually divert care from patients. And so along the same line, we did this work where we showed, and I'm going to show you a series of studies that are ultimately going to be showing, look, these deep learning models are able to pick up signals on patient images that are not very obvious to the human eye. And we need sort of more different thoughts to figure out why are they important. They're super important. They have a tremendous impact, I think, when it comes to population health, but we also need to make sure that we're cautious in terms of how we think about using them. So I mentioned that missing a code is actually, inequity, because then if you are saying, I'm going to refer the patient with diabetes to something else, then you cannot really identify that. The healthcare system is moving towards this value-based care, bundling codes together. For example, here you can see, you have a bundle for diabetes with acute complications, with chronic complications, and without complications. And this is being used to, the hope is that this is going to be the basis of how people get paid. And so, unfortunately, these are notoriously incomplete in the medical record. And so we looked at 6, cardiovascular diseases: congestive heart failure, atrial fibrillation, which just means a bad rhythm, obesity, COPD, vascular disease, and diabetes. And there's new work actually that is just showing how good the AI is for predicting atrial fibrillation. And what we find is that actually the model works well. These are not, unless I'm looking for a complication, these are not things that specifically for a radiologist that you would easily pick up. So it's this, again, opportunistic screening, but using the AI's ability to be able to detect some of these things to complete the patient picture, but also curate and relabel big data sets that allow us to look at health policy. So we did one more thing for this work where we incorporated the social deprivation index. And this is the most granular level zip code level ranking that is a mark of poverty and its associations with health outcomes. And so it tracks the poverty level, high school dropouts, renting, overcrowding, lack of car ownership, unemployment, all these factors into one granular zip code level. So if you live in a deprived area, for example, in this southern part of the US, you're in a more deprived area more than this area here. And what we did is that we incorporated that into the predictions. I mentioned that the model had, most of the things had an AUC of above 0.76. But when we start to probe this model into predicting a test case, in this is a patient, I mentioned language, because this is an area where, for example, if you have to collect a comprehensive history when there's a language barrier, the reality is that it's not complete. I know, the world of the consumer world has seen better translation things, especially, for example, if you travel, you can probably use your Google Translate to do that. But the reality in the hospital is that the translation services are not as good. And so, this is a patient who unfortunately had COVID, was diabetic, which was uncontrolled, just non-compliant with medications. But, the model kept saying, look, there's congestive heart failure. This is not someone, when you read this chest x-ray, you'd say they're in heart failure, but the auditing of the record allowed us to come to a point that, oh, this is someone where they had an echocardiogram ordered in the past, but just were never able to have it done. So some similar work related, this is just showing if you had ambulatory chest x-rays, these are patients, for example, you just have some chest pain, but it's pretty much, you're not in the ICU, but it's actually good for telling you who has diabetes. So we used around 270,000 chest x-rays from 160,000 patients. And this, on a prospective data set of around 10,000 chest x-rays, the AUC was around 0.84. And when we tested the same model at Emory without having to, retrain it, the AUC was 0.77. The prevalence of diabetes at the training site was around 16%. In the external validation, 5% of these patients subsequently developed a diagnosis of diabetes. So again, not something, unless it's a complication, that I would be able to say, oh, this patient is diabetic. But there's something that this model see, but you should be able to look at this work and say, wow, how's that possible? And then you should take it with skepticism, because we do need a lot more minds to look at this type of works to see, when it makes a difference and how can it really be translated to patient care. So in terms of explanations, imaging models are notorious for not being very explainable. And in this example, what we found is that the model was looking at the areas of adiposity, mainly around actually the clavicles and the subxiphoid area. Again, this is just the same area where they're light green, where the model was looking at and coming up with these predictions. So, people have used AI to actually narrow disparities. And this is this work by Emma Pearson and Ziad, who, we use traditionally this score called the Kellgren-Lawrence score, which tells you that the narrowing of the joint is getting worse. And it was developed from white male patients. And there's quite a lot of existing disparities when it comes to pain and how pain is treated and diagnosed. And what they did is that instead of labeling the knees with the Kellgren-Lawrence score, they labeled with the severity of the pain of the patients. And what they showed is that, using this algorithmic prediction, that they narrow the disparities for osteoarthritis diagnosis and narrow the disparities by race, income, and education. But they do one more thing, which I thought was pretty interesting, which is they look at eligibility for insurance, right? Because this healthcare provision doesn't occur in isolation. And this is going to be my second ask. The first one was thinking about outcomes, proper outcomes for us to think about when we look at image-based models, and even in the context of fairness. The second ask is, what's the so what, right? And here is that they show by just using this new score, we improve the number of people who get eligible for surgery. This is not unusual. This style of research is not unusual in health equity. For example, saying when we change the GFR, correction for Black patients, we change the people who are eligible for surgery. But it can also, by changing these metrics, we can also cause harm through overtreatment. And so that's another area of thought that requires just different perspectives. And I hope that you can help us answer some of these issues. So this work was done by UCSF, and they predict healthcare expenses of patients from chest radiographs using chest x-rays. When you look at this work, and I say this model here is considering the zip code, the income level, then you should not build such a model, really, because those are bias metrics. You're just going to learn a proxy. It's just like when you hear people say, oh, I'm going to determine who gets care based on zip code. The zip code encodes too much information. But what was surprising to me, anything with an X is an image involving model. X is actually just the image only model. And we see that the image only model actually has good performance. It's almost encoding, again, just like the social deprivation index, it's encoding some information that correlates to these markers of income and zip code. But these are not things that as a radiologist I can tell. In fact, when I look at this chest x-ray, where they show the low spenders and the high spender, this is a young patient, and I would just know that from my radiology training, versus this is a high spender for someone who has a chest pod. And in this incorrectly classified images, this is an old patient, and I know this because of their shoulders, the calcium in the aorta and the ectasia, which is just the shape of the aorta is changing. And this is just multifocal pneumonia. And I would think that this is a young patient, but you see, it's not consistent, but we still don't have enough things that allow us to probe, because the reason that I see this type of work being important is that we can use, if we had strong explainability tools, then we can use them to probe, to get hypotheses that allow us to study them well. So this is image-based algorithms. These are very, very common. And while these are published as biologic age, I would like to caution that these are main image-based age, not unusual for radiology. We do think about bone age, one of the earliest algorithms that was ever developed. And we also have chest x-ray age, like in this work, but we also have brain age, especially now as more treatments for Alzheimer's have come in. And what we see with this work is that they use a longitudinal data set, train a deep learning model to predict cardiac outcomes. And if your chest x-ray says, wow, wow, this patient is older than your actual age. And, then those patients were dead at the time of follow-up. And if your chest X-ray age says, oh, you're younger than you really is, those patients were alive. And so this different work published from a group in Japan looking at data from 5 hospitals. In fact, one of the hospitals, it's not unusual to get a chest X-ray as part of your screening examination. They show where the model is looking at in these hot areas around the mediastinum, which I would think that it's more of cardiac changes. But they use this generated age to predict the odds ratio of getting other diseases. And when it comes to like COPD, those are lung diseases, so that makes sense. But to me, what was surprising were things, for example, like liver cirrhosis, which is not something, unless you have decompensated liver disease, would be presenting in the chest. And so again, showing that some of these models are able to pick up things that are better than, and that we haven't thought about, but we still, without better explanations and better outcomes and better metrics, then we cannot really translate them to anything useful in the healthcare setting. This work looks at chest X-rays and inputs the pulmonary function test to say, tell me what the PFT is. This is would have been more important during COVID because you wouldn't be having people blow, especially just because of isolation and social distancing. And then also looks at the reports and see, is the image model better than the text only better? And they demonstrate the same, even the standard deviations for across multiple metrics that are important. But even more so, the image model is better for predicting severity of disease more than the text only model. The reason I show you this work is that in this case, you don't need to invest so much in the labeling of the report. It turns that if you just combine these two, you get a better result. But again, with some of the examples I'm going to show about how models fail, you have to wonder, is it good enough? Because then you can bypass the radiologist in terms of labeling some of these data sets. So the first part of my talk, I tried to show you why a picture is worth more than 1,000 words. I showed you from a chest X-ray. My own work has shown that you can tell the self-reported race of patients from just their imaging, that the patient is female. This is the chest X-ray age. They live in a deprived area. These are the ICD codes, and these are their healthcare costs in ways that we've not even been able to understand why this is possible, and how do we even utilize something like this. I'm going to quickly just show you some of my work for the self-reported race prediction from medical images. And this is a social and legal construct, not a biologic difference. And we do this across multiple data sets and show that you have AUC values of above 0.96 on chest X-ray to tell you this is from an Asian, Black, or white patient. But I'm going to show you just a couple of slides to show you why it's very difficult to do this type of work. The saliency maps that we rely on are very inconsistent. And when we block the areas where the model is looking at, we still find that there's signals in other body parts. When we use patches of the images, for example, in this area, we find that the model can still tell you what the risk of the patient is. And when we segment the lungs and look at the lungs versus the non-lung segment, we see a drop in the lung area, but it still has this signal everywhere else. When we blur the image and add noise, we see a big drop in the performance, but not close to the randomness of radiologists who we were performing around 0.5. And when we take pictures of pictures where we would think that maybe there's an interaction of some of the melanin or some of the biologic factors with the X-rays, we still find the performance is the same. More importantly is when we start to downscale the images like this 4x4 image, we still find that signal is present. And when we apply high-pass filters, like in this case here, then we still find that the performance is still, for the worst performing group here, in this case, white patients, the AUC is still around 0.86. It's not because of a specific piece of equipment, and it's not because of a specific anatomic and phenotypic confounder. So while I show you that image-only models seem to be better, they have tremendous opportunity for us to do this large-scale data set analysis, is that it still remains very difficult for us to study them because of the explainability tools and understanding what the model is looking at. And I'll show you an example of some shortcuts that the models, because the models are lazy, you know, so this is work that is pretty impressive. They take 2 data sets that they combine, they train models, and when they show them to the external data set, the model performance has significant degradation. They look at interpretation by doing 2 things, looking at saliency maps, which just shows you the hot areas that the model is looking at, and generative models. And what they do with the generative model is to transform maybe a positive patient to a negative patient. And for their saliency map, they see the same thing that we've known. AI cannot really tell pneumonia. It looks at where the images are coming from, for example, in the ICU, and says, oh, I think this learns the prevalence of the disease, and then makes a random guess. And when they start to change that swapping of the labels, they start to see that the model is still trying to track the radiographic markers to say, this is what I think is pneumonia. Compare this with this work that is the same work that is just saying, changing the last layer and saying, okay, tell me what the projection of the image is and what the patient sex is. And we start to find much better performance compared to the original one that I showed you for their disease prediction. For example, to tell you is this male or female, and it generalizes externally. And so one of the biggest challenges for us is to understand when we use these models, these image models that clearly we don't need to label them as much. We need to think about what the right outcome is, but in the understanding that the models fail a lot because of shortcuts, how can we really harness this for population health? Again, I started off by showing that images have exploded. We have a ton of images. In my institution, we image almost 1.6 million images every year. And this provide a big opportunity for, you know, is imaging the choice for health economics and outcomes research? Because we have widespread use of imaging. It's clear that the deep learning models are able to pick hidden signals at these biomarkers we don't know. And we even have potential for merging multimodal data, which gives us even a bigger sense of what's going on with the patients. And they don't require as much human curation, for example, body composition or calcium scoring. And it's cost effective because you're getting the image for something else, you know, and actually there is less radiation. And we've seen people even suggest, for example, some of our work to think about forensic pathology or completion of clinical trials when we are missing some of the data. But my ask and my challenge to you as we start to think about this deep learning on medical images is to think about the outcomes, because this is an area that today we use these metrics of AI that have really little utility when we think about the real world implementation. And what do those correlate to the labels, and what proxies would these images be representing, aka remember the zip code example, the social deprivation index. And then from an economist point of view, we need to think about the downstream effect. Are we going to be over-screening, under-screening, in fact, and how do we think about the cost, you know, the general cost and some of the consequences of large-scale deployment of these models. I'd like to end with some of the signals that can be really encoded in the data sets. It's clear that the models use these type of signals. Not everyone gets image. Black, Hispanic, and non-white patients are less likely to undergo diagnostic imaging in the emergency room if you present with the same symptoms, everything the same, just difference in race. And we know that some of the data sets come from, for example, safety net hospitals that may see a specific type of disease. And you know, and in that case, those tend to be very difficult, and it's clear now that those models encode the same. One other thing that I want to mention is that we're seeing new data set types. For example, Google released these chest X-ray embeddings, and they are actually computationally faster. They can allow us to move away from using ImageNet for the pre-training. But what we've noticed is that they still encode the same type of signals. And so as we move to these newer data sets and move to, I think everyone is now rushing for the next foundation model in medicine, that they still encode some of these characteristics, and we do need to be cautious and think about how to work with them so that they are beneficial for everyone. I started off by trying to show you some use cases that are amazing, I think, in a place where instead of saying, oh, I'm going to replace the radiologist, where you're showing, hey, you can actually supercharge healthcare by just leveraging deep learning for some of these cases. But I also caution in terms of these shortcuts that we don't understand when it's biologic, non-biologic, and what is one of the biggest limiting factors for us to largely deploy some of these things on a large scale for population health. This is one of the events that I held this year, just looking at bias and looking at some of these large data sets. We work on real world data sets from Emory University. It's a fantastic time. We're going to host the same event next year, so hopefully some of you will participate. I'm always hiring if this is the type of work that you enjoy. And here's my contact information. Again, thank you so much for the organizers for giving me an opportunity to present, and especially for being accommodative to allow me to present virtually. Thank you.
Thank you so much, Judy. That was fantastic. Now I think we'll move on to the Q&A section of our symposium. So I'd like to invite the speakers, Mike and Noemi, to come up to the front, and Judy's online. And I'd like to open it up to the audience for any questions you may have. Please raise your hand if you have a question, and we'll bring the microphone to you. There's a mic here. This one?
Yeah.
So I'll look at this here for you. Thanks.
I think we have to.
Yeah.
Yeah, let's just do it.
Okay.
Okay, go ahead, Doug.
Thanks. Great talks by everyone. Really interesting. So I had a question for Mike about the data poisoning. You spoke a lot about intentional data poisoning by malicious actors, but I was thinking about the degree of, I guess, poisoned data that there is in all of the training data that we use for the models. And I was just wondering if you could comment on how big of a problem that might be, because I guess I think about us reaching incorrect conclusions, and the mountains of data that the mountains of language that are sort of used in the training data that could be based on incorrect conclusions and mistakes could bias the output of these models. So I was wondering about, how do you correct that? Can you tell a model to ignore some previous conclusion that it reached? And if you could just speak about that a little bit. Thanks.
Sure. Yeah, thanks for the question. That's, I think, particularly for these large language models, that's much more of a danger, right? I mean, traditional supervised learning is usually working with a very curated data set, and the integrity of that is something you can readily evaluate. But I think when it comes to large language models, where you're essentially telling it to go out in the wild and soak up information, there's much more probability of that. I think the key is that there are techniques already proven around the tuning and reinforcement learning, where you can, you have to almost experience the exposure of bad data, bad logic, bad outputs and then figure out causal, what's the source of the information. So, but you can provide boundaries in terms of how these models are, what information they learn from, and you can also weight the validity or the credibility of the information in the instructions and tuning you provide.
So you can tell it to ignore or forget a specific thing?
Absolutely.
Okay, cool. Thank you. Yep.
Whether it behaves correctly is a whole different question, but
To Noemi and Judy, do you have anything to add on to the topic of data poisoning? No. Okay. next question.
Third for me, actually.
Yeah, I also had a question for Mike. I was trying to understand the hallucinations a little better. Are those like outlier events that are random, or are they things that can be tracked in the model and, reduced?
Yeah, they do tend to be, I wouldn't say random, but they are, relatively speaking, low probability events and outputs. So it's one of the reasons that, a lot of these, especially I think in healthcare applications, you need fairly rigorous evaluation and validation of outputs before you would release it into, real world use. So I think, with limited evaluation and launches with rigorous monitoring, you can detect the prevalence and classification of some of the hallucinations. And it almost goes back to, okay, what data is it relying upon to draw that conclusion or information? The other thing you'll see in large language models, it's a bit different too, is when they're provided in real world use, and you'll see this with like Chat GPT and Bard for traditional, is that they provide everyday users with the capability to feed back responses to the model to actually flag that, no, this is incorrect output, and provide that real world feedback real time. So it's another method I didn't mention in the presentation for controlling for that risk.
Josh.
I have a question to all, like anybody can answer. What are the privacy and security issues can arise with the use of AI in healthcare?
No, I mean, would you like to go first?
That's the next symposium, but that's okay.
Well, I mean, I can come first, but I'm not going to answer it. I think in research, whether it's machine learning or not, we tend to take data governance and data protection very seriously. So that's why it takes us years to get the get the data which we do research on. So I think that should keep happening, and I mean, I can talk from the side of the researchers, and I think if there is good data governance going on in our institutions, then I don't see any higher risks. But I do hand it to Mike, who might say something about industry and how they have it.
Actually, I'm going to probably take that question and direct it more at Judy, because I have to admit, during your presentation, Judy, one of the questions I had was, I think it's fascinating to think about the way we might use medical images perhaps for purposes not originally intended. How does that, like in your research that you've done, how does that work in terms of the availability and maybe privacy issues that might be involved in using images either for research or for purposes that they weren't necessarily originally intended for from a medical standpoint? Is that something you've had to deal with from an ethical standpoint?
Yeah, so you made the question a little more difficult, but the first thing is that there is a lot of work around anonymization and de-identification of images. And medical images are even a little challenging. One, because of this pixel information that they have, the bunting, leave alone the stuff that I'm showing. And ultimately, what people come down to is a statistical risk of re-identification. So it's saying that if I can pull all this metadata from your image and then I had like maybe your Facebook data or some other data, could I really tell that it's you, right? And so the things that people have seen can be tough, especially the head CTs we do and the head MRIs. These cameras are very good. In fact, so good that if you reconstructed the face and you walked out, you'd be like, oh, did I see that patient, right? It's very similar. And so we're seeing more of like defacing algorithms, and people are very, very cautious to release anything above the neck. There are other small things. For example, if someone did not remove a necklace or something on you, then it has your name, then people hypothetically could really just zone in and identify them. And so ultimately, I think people have ended up saying this is a statistical risk. Now, that being said, I want to go back to, one of the big push has been, let's release synthetic data in place of the original data set. And actually today I led a journal club where this group showed that you can really identify, you can go back to figure out what was the original data set. And so this area of, patient privacy is really just an evolving area, but just like was said before, we take it with just the utmost, privacy and standards that allow us to do this type of work. That being said, I think people hide behind, I don't want to release my data set for patient reasons. But we are in an era because of the Cures Act, maybe not your medical imaging, but you can get pretty much all your record in minutes once you're seen by the doctor. And people don't want to wait for the doctor. They're putting them on GPT. And so we're seeing some of the leakage of the PHI go on that way. And then the second area is in places where you're missing out and there's harm of not sharing data. And so ultimately, I think we should have better provenance, better governance, and the humility to understand when we don't know what we don't know. But I think today most people will use a statistical way. You'll remove the pixel, you'll have a human being review the imaging data. My group actually releases data set, and it's a very labor intense thing. And you have to learn all these things if you want to release a useful data set. And then at the same time, we have to make sure that we are really not hiding behind, let's not release data sets, because then the AI that will be built will not work for some patients.
I have a, just follow-up question on the topic of trust and building trust. So not so much about release of data, but the use of AI and ML for decision-making, healthcare decision-making. I mean, there's a lot of skepticism among researchers, among patients, among clinicians about using AI tools. And I'd love to hear from all of you. I mean, you've talked about the potential, but you've also talked about potential harms. And what kinds of standards do you think, and what are best practices that need to be put in place to ensure safe deployment of these tools and to build trust in them?
I'll go first, I guess. I think we mentioned that there are some work in standards and regulation in this space. And if you look at traditional tools that are used in healthcare today on the pharma side or medical devices, they have a lot of standardization around disclosure of information that includes risks, contraindications, et cetera. And so I don't really see this as being much different. I mean, the ability to provide transparent information and clear information is going to be a challenge in some of these applications, but there are people working right now on standardizing how to provide information and it also depends on the stakeholder. If it's a patient versus a clinician, they might need different information to make good decisions. But in all these products, it's going to be the same thing. There's no situation where the risks that we talked about will be zero, right? You can reduce them to a certain level, just like Judy was describing with the probability of, re-identification of images. You can't de-identify something to an absolute, no probability. But as long as people understand what that level of risk is versus the benefit that they get from the product, then I think that's your objective. But we all have to work together to figure out how to standardize the labeling, basically the information to describe the products or the applications. So.
Thanks. Judy,
Yeah, so I think that in medical, at least radiology AI, we had settled, right? People had realized, this is pretty hard to do. Then GPT came, and now we have AI influencers again. So we are back to the hype cycle. And I think one of the things that really breaks trust is, the hype. I think it does more harm than good. And this is because of overreach. I mean, we did see a big drop in radiology when Geoff Hinton said, oh, we're going to replace radiologists. You know, not such a big giant says those type of things, and they're not, you know, people don't read them or listen to them. And so I think today what we don't know is how to properly deploy AI at scale in the clinical setting. And we're seeing this with examples, some of the earliest trials, and this type of work is really difficult to do because where we're doing these human trials, and what we observed is that there's a recent paper that just got published in radiology that is saying, if your AI provides the wrong output to your radiologist, even the best, your most experienced radiologist, you bias them. And so now we're having a lot of problem with automation bias because you don't want your most experienced radiologist to be, you know, to have a drop in performance. And, you know, when we think about the true value of AI, I think even just looking at our real world implementation has come from not the intended value of AI. We have a shortage of radiologists in the US, and what it's come down to is I don't want you to have a chest x-ray that was done 7 days ago and there's a big finding there and I haven't told you because I just haven't gotten to it. And so if an AI can sort of flag some of these urgent cases, then it's turned out to be one of the biggest value adds that it can. But that's not why those systems were built. So in this era where it's still autonomous, we don't have autonomous AI, there are some approved products. I think for us to think about trust, we don't, you know, there's always this debate, do we really need to understand what the model is looking at versus not? I think the reality is that we cannot really have good tools that allow us to do that. But I think that we need to understand how AI fails, and we've not been able to do that because we're not deploying AI in that type of scale.
Noemi?
I try to answer this question from a more narrow point of view of using these machine learning tools in data science for HEOR. And I am part of a few conversations back in England when the National Institute of Clinical Excellence, which is not really the payer, but more like a decision maker body, is trying to understand where machine learning will come into the reimbursement submission, the reimbursement decision making process. So they are expecting pharma companies to start essentially employing machine learning to perhaps maybe cherry pick results, perhaps submit a model which is completely uninterpretable, and they worry that might actually bias decisions because they won't be able to review them. So they are asking for academics to somehow start brainstorming about how to come up with transparent reporting standards to make this process somehow better, and that would really help to really help prevent harm. And one thing which came up so far from these discussions is that academics could really help by creating these reporting standards, by publishing papers in which they are really putting the pros and cons of using these methods in understandable forms. That helps with capacity development within the industry, within the decision maker side as well. But for that, academics actually do need funding. So governments, national funding bodies could really step up and start prioritizing this sort of research. And that I would be very happy to do some of that research if there is funding for that.
Thank you.
Thanks. My question's for Noemi. Thinking about kind of the way forward, you talked about some limitations of machine learning and causal inference, but you spoke about one of the issues is that there isn't the counterfactual, but we have some methods for estimating the counterfactual to try and sort of create that group. Is there a way forward where you marry those two concepts, sort of create a data set that has the counterfactual and then do it, or just kind of thinking about that aspect?
It would be really nice to combine data which come from maybe randomized trial sources and come from observational sources, and maybe we could do something clever there. But there's not a lot of mature methods out there for that right now. So again, it's a space for methods development for those who are looking for PhD topics.
I can ask a question, and this is for Dr. Gichoya. I think you mentioned that, you have this image for chest X-ray or something like that, and that's predictive of a bunch of different other outcomes that was not the intended consequence. It reminds me like when the genetic genomic revolution came up, the genomics was used to do all sorts of incidental findings. And the real question was, should we intervene on some of them? So really the path from information, in this case, image, to outcomes is through decisions that we make. And to me, drawing from Noemi's talk, at that point, there needs to be some causal inference involved, like, okay, this information is generated, should I intervene or not? And the question is, how do you, in your clinic, kind of, design the clinic in a way that you could study these decision-making in a randomized fashion so that you can really learn from when to intervene and when not to?
Real world practice is very difficult, right? So I'll give you an example. My students trained a model for postpartum hemorrhage, and it was a good learning exercise, but their best performing feature was weekend. If you deliver your baby over the weekend, you're most likely going to bleed. It tells me that the models are able to pick up just patterns of how we work. And so I don't know that I think what we can do today is use explainability tools to help us probe the models to generate hypotheses, and then use those hypotheses to design the study that we want. But I don't know, for example, how you could change the weekend delivery. And I figured it's just because we don't have enough staff over the weekend or the night. But that's like was the most important model. It didn't matter how you changed it. And so, it just, for me, it's just so difficult to do the practice of medicine because, for example, if we have a clear outcome, this is something that I'm thinking about a lot. For example, if you say, hey, here is a cardiac segmentation, it's going to tell you, calculate for you the ejection fraction. Then in medicine, we know what to do with ejection fraction numbers, but there's no linkage of AI metrics today with a meaningful outcome. So you don't tell me this is a small pneumothorax, this is a big pneumothorax, this is a medium pneumothorax, which have different interventions. You just say there's pneumothorax or no pneumothorax. You don't even say which side it is. And so there's a big gap, in my opinion, that exists today from the mathematical metrics that are used. It's because sometimes it's just a finding. It's not just that, it's not because like this causes this, because I think that would be very difficult to do. In fact, some of the things we treat today in medicine don't have like a clear causal relationship, And so I think that would make it that we would never be able to use some of those tools. But in understanding, when we are looking at big data sets, some of the hypothesis generations, then we can have a look back at our own practices. And sometimes it's not that the technology is going to fix it. It's because we use the technology as a way to probe and generate new knowledge and new insights. Today, I was discussing with a colleague, and they say they're doing this work that shows all the females when they're using a large language models to extract notes, and all the females with headaches get Botox referrals, and all the men go to the emergency room. Imagine like as a practice, you would never think, I said, you tell me what happens when you tell your doctors this is the finding. You would never be able to even have this type of research or even outlook of your own practice if it's not for some of these supercharged models. So it's a very political answer. I don't know, maybe Melanie has something different in terms of structuring real world things, but if you just think about imaging and the downstream number of people who have to use the imaging, it would be impossible to design what was the real intent and what you're finding if it's useful. And we just have to think about more larger outcomes and tie them back to the metrics and our labels of the data sets.
It's a question for Naomi. I really appreciate your honesty in showing us or, explaining some of the potential obstacles that you encounter in your own research. As a researcher, I think we've all had that situation where we see something that's really counterintuitive and then we're trying to figure out why. So I was really interested in an example that you showed about the distribution of the impact of health insurance. And then you mentioned several possibilities. It could be just that that's the real world effect, or that's data pitfalls, or that's just wrong assumptions. So I was just wondering, in the machine learning study context, what are some of the common diagnostic approaches that you would employ in this case to rule out, which scenario would be causing a problem, things like that?
That's a really hard question. I think that for example, checking the violations of your causal assumptions, we could go to the more traditional kind of econometrics tricks, like, for example, looking at the impact on some outcome which shouldn't be affected by the treatment. And again, if you find some effect there, then maybe your model is not working. We haven't done this for this paper yet, but maybe we should. Yeah, and in terms of what constitutes as good data, I don't know. I do think that there's a lot of space for qualitative assessments that, like, actually going back to those who understand the context, and I think that is what Judy was also talking about, that these surprising findings mostly require sort of talking to people and trying to understand it.
I just want to expand on some of this conversation. And this is a question is for Judy. I want to know, I'm wondering if you can talk more about the predictive value of using AI in imaging, because from my perspective, if it doesn't get it right 100% of the time, then that causes serious harm to the patients. And it obviously adds to resource utilization and to the problem of overdiagnosis. So I'm just wondering if you can talk more a little bit about that.
I think the value really has been unintended. It's really been to workflow of radiology, and where, for example, sometimes we have studies that haven't been read for 7 days, right? So you don't want to be sitting on a brain bleed and the patient went home and you haven't intervened on them. And so I think it just nudges the doctor to maybe look at, you can imagine like how we work, we have a big list of hundreds of cases. So if it's like 500 and you're just working through down, that 500 case comes up and then you can take care of it early. So it's okay if it's not accurate, because it's not the end of the world. But if it's positive, we want more sensitivity to just make sure that you're catching everything. When it comes to, there is AI that is actually used, but we don't really interact with it that way. And it's around image processing. And that's been super helpful because it has improved the speed of the scanners. It reduces radiation dosage, right? So it's used in the pre-processing. And we're very blinded to that because previously it was still algorithms. They were not just deep learning powered. But I know quite a lot of companies, for example, with the low field MRI, very bad images, but they use AI to make the images look better. But that MRI is portable, and sometimes moving patients can be a big harm. And so I think most of the benefit has really come along this like sideline, what's called the non-interpretive uses of AI, more than you're better than radiologists. In fact, all the studies that have looked at that, they show that AI is not as good, and it doesn't make radiologists faster, which was the other thought that people thought it would be, just can cause automation bias and is more of an interruption. So I think we still need to understand how to deploy the AI better. For example, maybe I never need to see the result unless there's a big conflict by the time I'm signing the report. But we don't know that. And most of the use cases have just been on the sidelines, things that just are needed to make sure that that you're not getting into trouble or patients are not being abandoned for a long time.
There's a question here.
So I have a question, Noemi, for you about you shared an interesting example with the study you did with the data from Indonesia, right? And the reliability of the underlying data that's there, right? You did all of your studying. At the end of it, it was starting to question, well, these results don't make sense. So is the data right? Were we looking at the right data? I'm wondering, with your experience with the University of York, any partnerships with the National Health Service, right? Is there any questions that they're asking, they're trying to drive down? Because as a nationalized health system, right, everybody is, well, more people may be involved as opposed to disparate health systems, private insurances, people that refer themselves to certain hospitals and don't. I'm wondering if you're seeing a more completeness of data, or if there's any work with them currently that you can highlight.
I don't directly work with the NHS data, but I think I can maybe give you some answer here. So there are some data sources, most prominently the so-called hospital episode statistics, which is records of every patient admitted to the hospital, which is extremely complete and is very good quality. And my colleagues have a lot of experience working on this data. Yeah, but I think like this data doesn't necessarily have all the information which researchers might want to answer. In the UK right now, there is still a really big reluctance towards data linking. So there will be like maybe single data sets used again and again for answering questions, but it is currently not possible to, for example, link someone's hospital records with their private appointments and perhaps some other piece of information which will be very helpful. And I think this is going back to the point of the extreme sensitivity to privacy, which might be a particularity of the UK health system, and real worries about identifiability. Yeah, so there is some good data available, but it's not showing the complete picture of the health system, which is more complicated than just the NHS.
Okay, we are almost at time. I'll take one question from our online participants. And so I'll read the first one I have here. Do you foresee the use of generative AI in the healthcare space to follow a similar path to computer-aided detection devices, where the initial approach is in supporting the clinician, and it is yet to be seen when computers will become the decision makers? Or is generative AI going to be the tipping point where the algorithms are authorized to be decision makers?
Yes, I'll take that one. Yeah, I think, no, I don't really foresee generative AI or large language models being the decision maker, not anytime soon. And the reason I say that was actually interesting. We have the chief clinical officer at Google's pulmonologist, Michael Howell, was interviewed by JAMA on a podcast recently, and he was asked the question, do you see these tools as replacing doctors? And his answer was no. But he said doctors who embrace and use this technology will replace doctors who don't. So in other words, it's still going to be a very, ideally, a very important tool, but just like, CADI technology today, it's typically augmented to the physician's use, and it's not replacing their decision making. There's a few cases where you can see full closed loop decision making, and there could be a situation like that. I mean, automated external defibrillators are a good example where they're analyzing ECG and they're deciding to provide therapy, right? And so there are probably some very narrow cases where we might have exceptions, but I don't see it on a broad scale anytime soon.
Can I ask? So we have discussed a lot about AI, but we haven't really discussed anything about the economics of it. And data generation is not a costless process. And more importantly, the data generator is more and more monopolistic in the markets. And so what do you think if these large language models, which rely on actual data, would then end up in hands of a few entity who monopolize the data generation process? And what would be the implications for that for the overall healthcare and the society?
Who would like to take that one?
Over some wine.
Yeah, I'll try to take a first cut at that. I think that scenario would be obviously very problematic because we've already talked about inequities, bias, et cetera. So any type of over-directive control of the data set would be something I think the general community should steer away from and do what we can to put barriers in place to that. I do think that the economics of AI, and actually we talked about this a little bit before we even started the conference, the health economics, particularly in the US of the medical system, is very complex. How things get paid for, what the incentives are, who the decision makers are and the drivers often gets in the way of great technology and great opportunities to make moves forward in healthcare. And so I think one of the biggest challenges really is trying to determine it. And it's not unique really to AI. It's just any new idea that has great potential for improving outcomes seems to sometimes get caught up in trying to navigate who's going to pay for this, who makes the decision to use it. I mean, even Judy's example with images, like what's driving that increase in images? Who's paying for those? What's the justification for those? And there's a lot of factors that go into understanding that. So any particular AI use case is going to have a unique set, I think, of questions around to answer that point. But
just one comment to that is we haven't seen many cost effectiveness studies. But I think there has been interest, especially in the UK, where that's how like something gets compensated. So we're going to see some regional differences. For example, is it easier if I screen you with AI or not? But in the US, remember, there's also a lot of lobbying, right, for professionals. So the technology may get there, but the society and the political changes may not. And so it's not just because the technology is not getting there, but I also would like to say the cost on society for training this data, curating data sets, the incentives, the public-private partnerships that are required. For example, insurance companies, some of the work that I showed you, people are purchasing the chest x-rays and using them for underwriting or starting companies to do the same. Some of the, ultimate things that we need to be thinking with more of like an economic lens, and especially thinking about incentives.
I guess being a health economist, I have to maybe I have to say something here. So I recently got invited to give my views on updating the CHEERS reporting guidelines for AI as medical device sort of product. So essentially, any technology which has an AI component, if we do cost effectiveness analysis, there might be some new complications to take into account. And one of the complications might be that these models, which Mike and Judy talked about, they are kind of living entities. So the input parameters which goes into a traditional or more traditional economic evaluation, they tend to be, relying on maybe a trial, a set of assumptions, which was kind of by the time of publication that was that was accepted. When it comes to AI, then that's a model which is continuously trained. It might change over time, and that snapshot of time where the data is generated may absolutely not reflect the reality when the product would actually be rolled out to actual patients. So there's a lot to think about there, and I do think that again the health economics community is trying to think about this and trying to come up with the challenges which have to be solved, partly by us, partly by others.
Thank you.
Well, on that note, we will adjourn. please thank me or please join me in thanking our speakers. Thank me. And for those of us joining in person, there is a reception upstairs in the Vista Cafe. Those of us joining online, thank you so much for joining, and hopefully we'll see you in person soon. Okay, thank you all.